So let's start with the content. Now, like I told you, here we again have the big picture about computer systems, put in a slightly different way than what you saw earlier. But this one has a lot more details. But what we had a look at earlier was very simple to differentiate between hardware and software and the dependency of your compiler to your instruction set. So here we have everything about a computer system, a cross section of a computer system, if you will, right? So you can see there are different stuff here, starting from problem, algorithm, programming language, compiler, assembler, blah, 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 and down to microarchitecture. And the microarchitecture itself is composed of these little things, these other things down here, functional units, gate level stuff, and then down to transistors and semiconductors, right? So this color scheme is described here at the bottom right corner. The gray stuff are human related things in a computer system, and the blue stuff are called the system level. The red, all these orangish things are called RTL, or registered transfer level. And the greenish one is called logic level. And the light gray one here with red text is the circuit level, and the other one, the black one, is substrate level. So as you are already familiar with, computer systems, be it purely software or including hardware, anything, computer systems are built to solve problems, right? You build a system to solve a problem, as in any engineering system. The computer systems are also built to solve problems. So you find problems which you need to solve, and you build a solution for that problem in the form of an algorithm, then use some programming language to convert that algorithm into a binary image or machine code using a tool chain, using a set of tools, compilers, assemblers, linkers. There are a host of tools involved here to translate your program, which you have written using some programming language like C or Python or whatever, into machine code. And like we discussed earlier, this machine code is intended to run on a particular CPU type or particular microarchitecture. So the microarchitecture is dependent on something called an instruction set. We call it instruction set architecture, ISA. An instruction set architecture is a specification which defines what the computer will understand, right? Basic things the computer will understand. For example, adding two numbers together, you need an instruction for that. The computer needs an instruction for that. So you can have an instruction saying add one number from one register with another number from another register and put the result in a third register. You can have an instruction like that. That is something very specific, right? So, very well defined and very specific instruction which the computer will be able to understand. So an instruction set will contain a large list of instructions like that. Not necessarily large, let's erase that. A list of instructions that the computer will be able to understand, right? So the whole idea is you as programmers should be able to write programs based on these instructions given in an instruction set, and then run that program on the intended type of microarchitecture, right? Like the previous example we took, if the instruction set architecture is ARM version 8, it will specify a list of instructions that a computer which is built based on this ARM version 8 instruction can understand. Those instructions could be something like add numbers together, subtract one number from the other, multiply two numbers together, or load a number from memory into the CPU, or store a number from the CPU into the memory, right? All kinds of different basic activities will be well defined in that instruction set architecture. So the computer, the actual microarchitecture, is a circuit which is built to support a given instruction set like that. If the ARM architecture contains, let's say, 10 instructions, for sake of simplicity, 10 very specific instructions, then an ARM-based microarchitecture will use various digital electronic circuits to support all those 10 instructions in actual hardware. At the same time, you need to write programs using those specified 10 instructions in that hypothetical instruction set. So you can run your program on that microarchitecture. Okay, so how do you write programs using instructions? If you write programs using instructions, you are either writing using ones and zeros, machine code, you write your machine code yourself, which is very, very difficult, or else you can write using textual instructions like, okay, add two numbers together, subtract one, and then multiply by some other number. So you can use textual representation of these instructions. That is called the assembly language, right? So you can write programs using assembly language, which you will be doing in the labs here. But again, for very general purpose things, writing programs using assembly is difficult. Writing large programs using assembly is not that easy. So that is why you have programming languages, different types of higher level programming languages, and related tool chains. So for example, if you take the C language, you can write a program for your algorithm, whatever the algorithm that you want to convert into a program, you can do that using a programming language like C. And if you use C programming language, and if you want to build your program such that you can run it on an ARM processor, you have to use the ARM toolchain, like the ARM GCC compiler toolchain. So that toolchain will compile your C code into assembly code, and the assembler, the associated assembler, which is again built into the toolchain, will convert your assembly code into machine code. The linker will add some more things into your final built image. We will learn those things later, right? We'll learn about these things later, the details about the instruction set architecture, microarchitecture, all these things we will learn in this course. So far, you are familiar with solving problems using algorithms and using programming languages to write source code for such algorithms. And of course, you are familiar with some compiling tool chains as well, since you already have done programming, right? So in the previous courses like GP106 or CO222, you have learned about some of this gray and blue stuff here, even in the system level. So then in this course, we'll learn more about the instruction set architecture, microarchitecture, and some stuff in the system architecture. So before we get into the system stuff, let's have a look at what this microarchitecture part includes based on the stuff that you see at the bottom here, right? So like I told you, microarchitecture is basically a digital logic circuit built to support a given instruction set. So when a compiler toolchain will give you a binary image for the same instruction set, your microarchitecture should be able to process this binary image, understand this binary image, what are the meanings of these ones and zeros, and do the necessary operations in actual hardware, right? So in that sense, the instruction set architecture is the key point which combines the software with hardware. So in a computer system, arguably, the instruction set architecture is the key place which provides the interaction between your software side and your hardware side of the story. Now, like I said, let's have a look at this microarchitecture bit a little bit. So it's a logic circuit, like I said. So what is it built up of? It's built up of functional units or building blocks. Functional units are building blocks based on logic circuits. So what are these functional units? Now you're familiar with adders, these triple carry adders, half adders, full adders, multiplexers, encoders, decoders, these stuff from your CO221 course, right? So those are the functional units which you can use to build a microarchitecture with. Microarchitecture is a larger circuit built using a collection of functional units with some additional gate level logic circuitry as well. So the functional units in turn, if you take an adder, it is also built based on gate level circuits, logic gate level circuit, right? At the gate level, you have AND gate, OR gates, NAND gates, NOR gates, XOR gates, right? You know what these different types of gates and how they behave. So using those gate level entities, you can build more complex functional units like adders and multiplexers, decoders, things like that. Using all of these together, you can build microarchitectures. Now, the gate level stuff, the different logic gates that you have, they in turn are built using transistors, right? There are different types of transistors, BTL, CMOS. You heard about these terms probably in 221, or you will learn about these things in your electronics courses. So there are different types of transistors, and the logic gates are built using these transistors. What transistors do is they manipulate current, right, or voltage levels, and based on that, you build logic gates where the logic gates manipulate logic levels, logic high, logic low, right? Ones and zeros start to appear at this logic level. At the transistor level, what you have is voltage levels and currents. So the transistors in turn are built based on different semiconductors, right? P-type semiconductors, N-type semiconductors. You combine them in certain ways and come up with transistors, right? The semiconductors deal with electron currents, and at transistor level, we say we are manipulating voltages. At gate level, logic gate level, we manipulate logic levels. At functional unit level, we manipulate numbers, right? Adders deal with numbers. So we manipulate some more higher level quantities called numbers. And at microarchitecture level, when we put all these things together to build a microarchitecture, we manipulate instructions, right? So all these things are conceptual things, where voltages, logic levels, numbers represented in computers in circuits, and instructions are conceptual things. And based on these instructions, everything about software is built, right? All the software that you will build and learn about, whether it's an artificial intelligent thing or whatnot, is based on instructions. It boils down to instructions at the very lower level of software, which are understandable by microarchitecture in hardware. That is the interface between hardware and software. Okay. Any questions here? Any questions at this point? Okay, right. So now this is mainly for the computer engineering students here in the class. So in your computer engineering degree program, this stuff that I shaded in yellow, you have covered for the most part in CO221. And yeah, the mechatronics students have also done that as well. So the functional units like adders, multiplexers, so all kinds of different logic circuits you learn, right? Gate level design and how to build functional units using gates. All these things you have done in CO221. And these transistors and stuff you will be learning in the electronics courses. So the lower level, at the very lower level, the concepts you will learn in the electronics courses. In this course, in CO224, we will be mostly dealing with this part of the system level. Instruction set architecture is something very important that we will be learning, and microarchitecture, how to organize a circuit using functional units to understand the given set of instructions, that we will learn, and some related systems architecture content as well, like memory, how memory is organized and built, how to use memory, then how the components are interconnected in a computer system, interfacing between different hardware components, and some abstract concepts like virtual memory, operating systems also we will be touching upon in CO224 in this course. Then the other courses, of course, in your previous semesters, GP106 and CO222, you learned about programming, algorithms and programming, and a little bit about compilers as well. In CO224 also, we will be learning about assemblers, linkers, and that part of the systems level as well. We'll be touching upon those concepts. So in the third year level, CO3 to 1 is embedded systems. You will learn about this entire computer systems picture, the big picture, but with certain constraints, which are coming from embedded system. We'll not talk about that right now. And you will learn about data structures in CO3 to 2, which are again in this algorithm and programming level with some emphasis on memory. Then you of course have networking. Networking is a sub cross section about this entire computer system, right? It's a part of the entire computer system, starting from the substrate, the voltage levels, even down to that at the very bottom of the communication, up to system and human application levels as well. So The computer networks courses will cover a complete cross-section of the entire computer system, targeting on communication aspects. Then in other courses like CO3, 2, 4, 5 and all, you will learn more about software, operating systems, application software, so different higher level abstractions you will learn more in the 3-2X courses, other 3-2X courses. So 5 series courses which you will learn at the very end towards your semester 6 and 8. You will learn some advanced concepts like artificial intelligence, machine learning, advanced concepts about computer architecture even, or advanced concepts about programming. So advanced stuff you will learn in these 5 series courses. So that is the big picture of a computer system, and how you, mostly computer students here, will be learning parts of this computer system throughout your degree program. So I will ask you to come back to this big picture. Every time you learn something new in the upcoming course, come back to this big picture and see how what you learned connect into this big picture. Where is it? What is it about? What is the value it's adding? Right? So come back to this big picture and try and connect whatever you learn in the future to this big picture, because this big picture represents everything about computer systems. As computer engineers, you should have a very good idea about this entire system, from semiconductors, transistors, up to problem level, application level things, and everything in between. Okay, right. So now, in this course, like we discussed, we will be using the book Computer Organization and Design, which is uploaded in your fields page. You can go and have a look at that, download it, refer to it. And we will be going through a number of chapters from the book itself in the classes. Now, this chapter 1 will be about computer abstractions and technology. Abstractions we already started talking about, right? These voltages, logic levels, numbers, instructions, all these things are abstract concepts. Concepts that we have created with certain definitions, right? So we'll talk more about that, and we'll talk more about the technology used for computer systems and how they evolved historically to the current state. I'll be taking up that topic. Then we'll talk in detail about instructions and instruction set architecture, which is basically the language of the computer, right? Like I told you, that is what the computer understands. That is how a computer is built. The computer is built to understand instructions, right? So that is their language. So that we will go into a lot of details, and Professor Raghal will be taking that topic. Then arithmetic for computers. Different types of number representations, I'm sure you learned in GP 106, like how integers are represented, or how floating point numbers are represented. So you know about this. So we'll not discuss about this in the classes itself. Instead, we'll give you this as a self-study assignment, how computers deal with these numbers. So you can refresh your knowledge and learn a little bit more in that topic. We'll do that as a self-study assignment. Then in chapter 4, we'll talk about the processor, that is the microarchitecture, how a processor is organized in order to support a certain instruction set. And now in this, in chapter 2, we'll be using ARM architecture, ARM instruction set architecture as our example. And in chapter 4, when we are organizing and we'll be actually building a processor in the labs there, we'll be using the MIPS architecture. So you will get to learn about 2 different architectures in the course. And in chapter 5, we learn about the memory hierarchy, how memory is organized and how it is instrumental in letting the processor process instructions. And in chapter 6, we learn about storage, secondary storage, like hard disks or other secondary storage types, and I/O, inputs and outputs, and different interconnects, connecting different components of a computer. And in chapter 7, we learn about multi-core or multi-processors and many processor systems where you have hundreds of processors even on the same chip, clusters and things like that. In chapter 7, we'll learn about those things. So from chapter 4 to chapter 7, the lectures will be done by Dr. Radhakrishna. And for the entire thing, I'll be doing the practicals for you with the help of our instructors. Right, so in the labs, we'll be writing assembly programs for ARM instructions architecture in the first half before the mid. After the mid, around week 8 or so, we'll start the microarchitecture practicals where you guys will be building your own processor, own CPU using Verilog HDL along with memory, assembler, cache memory and everything. So you can actually run programs, run assembly programs on the processor that you build, right? So that is what we'll be doing in the labs. Right. So you will learn here, like we've been talking, how what happens to your program once you write a program, how is the hardware going to run that program or execute that program. You learn about these things, and you will learn a lot about the interface between hardware and software, which is the instruction set architecture, right? I told you how key that is for us. We learn a lot about that, and performance is a theme that we'll be touching upon throughout this process, right? Performance, how well, how efficiently, how fast can your CPU do things? How can it be improved? That is something that we will be talking about in every topic, starting from the first one. So, yeah, how to improve performance through hardware design, we'll be talking about throughout this course. And at the end, of course, like I told you, this parallel processing, multiprocessors, multi-core processors, many core processors, these things we'll be learning in this course. All right, so the first topic that we'll be covering today in today's class is about 25 or 30 minutes remaining. In that 30 minutes, we'll talk about these different abstractions. We'll talk more about these different abstractions, right? We already started talking about them. We talked about how voltages are abstractions, how numbers or logic levels are abstractions. We'll get to that. So that is what we'll be covering today. And then next week, I'll be talking about these other stuff, technology trends, and all these other things about the history of computer processors and performance. We'll talk about in the next week, right? So let's get into today's remaining part, which is computer abstractions. What is an abstraction? What do you understand when you hear that word? What is an abstraction? Anyone care to make a guess? Or if you know some solid answer, can you give it? What is an abstraction?
Trying to overcome the complexity of something, like not looking what's under the hood, but what's over it. Something like.
Yes, Adib, exactly. That is a very good answer. Ashan, were you going to say something?
No, sir.
Okay, right. Yeah. So Adib's answer is very correct. So trying to not look into the internal details about something, and as well as not try to worry about what is at the top. So we are talking about something like hierarchy, right? Hierarchy of things, abstractions. Let's say there are things, some things, hierarchy of them where there are upper levels, lower levels, and at any point in this hierarchy, when we talk about the thing or the abstraction at that level, we'll not worry too much about the details underneath. Those details are hidden, and we'll also not worry about what's above it as well. So you encapsulate the details and hide them and define certain characteristics or qualities to identify that abstraction, right? To give some meaning to that abstraction. So this doesn't apply to only computer architecture, this applies to everything. So far, we've talked about different abstractions already. So I'm going to give you an exercise here to arrange the abstractions. I'm giving you a list of abstractions, and I'm going to ask you to organize them in some meaningful way, in some hierarchy that these abstractions make sense from the top to bottom, right? So let me bring it up. Right, can you see the screen? The document I'm sharing?
Yes.
Right, okay. So here, this is the list of abstractions. You can see how many, like 10, 11 different abstractions here, different things. What I want you to do is take a piece of paper, or you can bring up a Word document or a draw.io page or whatever, and arrange these abstractions in a meaningful way, in some hierarchy, right? Like he said, each abstraction we are trying to build it based on some other abstractions, but we are hiding those abstractions at that level. We are not going into details. So your organization should make sense like that. At each point, there should be stuff that are at the bottom and stuff that are above. And the connection between these entities at the hierarchy should make sense, right? Can you try and organize it? Organize these things in a hierarchy, in some hierarchy. It doesn't need to be something sequential. You can come up with whatever sensible way, right? There's no one correct answer here, but the way you put together should make sense. How can these be connected to others? You have functional units, programs, logic levels, numbers, algorithms, gates, substrate, transistors, microarchitecture, all kinds of different things that we talked about so far. All of these things are conceptual, right? All these things are conceptual. Concepts, abstractions, which are hiding details underneath and providing some services to the things that are above, more higher abstractions. Let's take about, let's say, what time is it? Okay, let's take 5-6 minutes to get this done. You can write it on a piece of paper or in a Word document or whatever you want. I'll ask you to share what you come up with. So you can share your screen or point the camera towards whatever you draw on your paper. In the meantime, of course, if you have any questions, please feel free to ask. Okay, I'll pick someone from the list. Harita? Harita, can you show what you come up with? I'll stop sharing. You can share your screen if you want. Or you can turn on the camera and show if you wrote on paper.
So can you see my screen?
Yes, Harita. Right. So you start with the substrate, voltages, transistors, okay, logic gates, logic levels. Can see a pattern here, yeah. So functional units, microarchitecture. Architecture is built on functional units. Functional units are built using logic gates, and logic gates are built using transistors. So yeah, I can see a relationship forming throughout these things. And algorithms, data structures, machine instructions. So towards the bottom, you have more software stuff, and towards the top, you have more hardware stuff, right? Okay, so that's very good. That's quite good, and a lot of things are very correct here. But you could maybe try and organize it in a slightly different way to add even more meaning than this. The meanings are, I think, somewhat clear, but say, for example, logic levels, what does it mean at that point in the hierarchy? Or does it make sense to take it out at that point and put it in a different way to make more sense? Even more sense. But what you have here, it makes a lot of sense, but you could even make even more sense. Good job, Harit. Very well done. So let's give a chance to someone else. Shamil? Right, okay. Okay, that's interesting. So you have the hardware stuff at towards the bottom and software towards the end. So let's start from the bottom. You have the substrate, like, okay, silicon or whatever, the semiconductor, and you build transistors based on top of that. And you build logic gates using transistors. You build functional units using logic gates. And you build microarchitectures using functional units, right? So yeah, that is very correct. And then on the higher side, on the top part, you have machine instructions. The connection between machine instructions and microarchitecture is not the same as what we had in the bottom, right? It's not machine instructions are built using microarchitectures, but microarchitectures understand machine instructions, right? But from there onwards, programs are built using machine instructions, and algorithms are represented using programs. So yeah, very, very good. And on the right hand side, you have these dotted arrows. So transistors and voltage levels, there's a relationship, right? What is that relationship? It's like transistors understand voltage levels, right? You can say, put it like that, or you can put it like that: transistors deal with voltage levels or interact with voltage levels. Logic gates interact with logic levels, or logic gates deal with logic levels. Functional units deal with numbers, right? So that makes a lot of sense. right? What you have here are two different hierarchies, let's say, which are connected to each other, right? So logic levels have some form of relationship with voltages, right? Numbers in turn have some form of relationship with logic levels, right? So what you've done a really good job here, Shamil. And I would only make a very couple of very tiny changes to make even more sense out of this, but this is really, really good. Well done.
Thank you, sir.
So let me go back to my slides. Right, so these were the abstractions we started with, and this is how I would organize it. So, as you can see, what you've done is nearly the same with maybe a couple of tiny differences, right? So what you both of you guys, Harita and Shamil, and I'm sure most of the others all of the others did the same same job as well, similar jobs as well. So done brilliantly. So this is how I would organize, and this is very similar to what you had done, right? You have the substrate, silicon or whatever, germanium or whatever substrate that you use to build semiconductors, transistors at the very bottom of the hardware hierarchy, right? So what you have on the right-hand side here is the hardware hierarchy. You have silicon or whatever the substrate, then transistors built using those semiconductor substrate, logic gates built using transistors, functional units built using logic gates, and microarchitecture built using functional units and other logic elements, right? So the hardware hierarchy is what we've been talking so far, and it makes sense, right? At each level of this hierarchy, what you have is an abstraction, and that abstraction is built based on other abstractions at the bottom. So, right, now on the software side of things, we have algorithms, right? That is at the very highest point. We have algorithms and data structures, which are conceptual entities we use to represent solutions to problems, right? We solve problems using algorithms and data structures. Then those algorithms and data structures can be represented using programs or collections of programs. Source code, like we've been talking so far. Then source code or programs can be represented using collections of instructions, machine instructions, right? Assembly instructions, if you want to look at them in a text-based way, or ones and zeros. Machine code, machine instructions, if you want to look at them in a binary way, right? They're the same meaning. The assembly instructions are a one-to-one mapping, have a one-to-one mapping with the corresponding machine instructions. So they're essentially the same thing. The programs are sequences of such machine instructions. Machine instructions in turn can be represented using collections of numbers. The machine instruction you will learn in due course have a collection of numbers, a sequence of different numbers represent a machine instruction and give meaning to that machine instruction, right? So numbers represented inside a computer are a collection of logic levels. Numbers we represent as strings of binary digits, right? So the strings of binary digits are collections of logic levels, right? High and low, or 1 and 0 logic levels. If we put a series of logic levels together, we can represent a number and give meaning to that number. Likewise, the logic levels themselves are represented using voltages, right? So logic level 1 is represented using a higher range of voltage levels, let's say 4 to 5 volts. And logic level 0 can be represented using a different range of voltages like 0 to 1. That range of voltages, those ranges of voltages depend on the type of transistors that you use, right? If the type of logic that you use is, say, TTL, the ranges of voltages are different to CMOS transistor-based logic gates, right? So there's a relationship like that between these hardware abstractions and corresponding software abstractions. So transistors deal with voltage levels, logic gates deal with logic levels, and all these things are interconnected. Functional units deal with numbers, right? If you take an adder is a functional unit, it deals with numbers. It can take two numbers and add them to come up with another number, all of which can be represented using ones and zeros, right? So functional units, some functional units may also deal with logic levels as well, depending on what type of functional unit that is. Then microarchitectures deal with instructions. Microarchitectures can understand machine instructions, that is, collection of numbers represented using ones and zeros. Microarchitectures can understand or make sense of such machine instructions, right? If you have an assembly instruction called add two numbers together and put the result in some register, the microarchitecture understands that instruction. So those are the relationships between the hardware abstractions and the software abstractions. These are very tightly coupled. You have a very tight relationship between these abstractions. So all these abstractions together makes a computer system, a complete computer system, right? So software side, starting from algorithms, you can deconstruct an algorithm down to voltage levels. And you can deconstruct a microarchitecture down to silicon PN junctions. So all of these things together, organized like this, allows us to create this concept called a computer, right? All these abstractions helps us build the abstraction called a computer system. And computer systems are everywhere now. So we'll be learning how computer systems actually work when it goes down this program level abstraction, right? When a program is broken down into instructions, how everything happens, right? How the hardware deals with these lower levels of the abstractions we will be learning in this course. So that's it for today. If you have any questions, we have a couple of minutes to take up those questions. If not, we can end today's session. Okay, so looks like there are no questions for now. If you have questions, you can ask in the chat group as well. And I asked you to do a number of things, especially related to the practicals, things you need to do before coming to the practicals, things you need to do by the end of today, like making the lab groups. So go ahead and do those things. And I'll see you on Wednesday. Thank you, guys.
Thank you, sir.